And I'm glad and happy to introduce to you tonight Joe Holmes. He is one of our members here at the hub. And Joe, why don't you just tell us a little bit about what you do and yourself, and then you can jump in. So he will present, and then we will definitely leave time for some Q&A. Additionally, if you're all right with it, if you have a question in the middle, you are allowed to raise your hand. This can be interactive. Yeah. So don't be afraid to interact. All right, Joe, welcome.
Thank you. I'm going to project if that's okay. I'm probably loud enough to not need this mic, but let me know if I'm not. So I'm Joe. My day job these days is a curriculum developer in AI and machine learning at Codecademy. In the past, I've worked at Quantic School, deeplearning.ai, some other places, making educational content, usually about machine learning, sometimes about web dev and stuff too, just generally like to code and fell in love with ML and AI. And yeah, the topic that we're going to get into today, just to give you a little background, is about the cutting edge or close to the cutting edge of where AI is these days over the past year and a half or so, and how we've built on the first iteration of ChatGPT into this brave new world that we're in now, which you'll usually hear the word agentic involved with. But I'll get into all that in a moment. Before we get started, could you just raise your hand if you would rate yourself kind of familiar with machine learning and its various terms, vocabulary, just kind of, you can talk the talk at least. Okay, beautiful. So I'm just going to start with like a little bit of background on some terms, but we can do this kind of fast since it does seem like most folks are kind of conversant already. So if you can see on the screen here, these are the two paradigms of ML that we're going to talk about. The first one is supervised learning, which is kind of the most common type of ML. It's the one that's seen largely the most success in business applications. But in supervised learning, you have a set of features that you feed to a predictive model. When you're training that model, you have labels, that is answers. They're the things you want the model to be able to predict. You train the model against those labels, and it gradually improves. And basically, it's compared to other forms of machine learning. You could say it's reliable. And then interestingly, for our purposes, it is often bound to the humans giving it data, or the data that it's able to use as labels. As we'll see when it comes to large language models, this is very interesting in that the large language models themselves, trained under supervised learning, know how to mimic human beings and human text, but not much else, and that'll become important later. Reinforcement learning, on the other hand, which isn't quite as widely used in business applications, not as widely known perhaps, has a totally different paradigm, and it's where an agent in an environment gradually learns something called a policy, that is like a set of instructions to act in different situations. And it learns how to update that policy based on being rewarded or punished when it interacts with its environment. This regime of machine learning, which is sort of what frontier large language models have started moving into more and more over the past couple of years, is tricky, it's buggy, it can be difficult to get right, but it's very powerful in some very interesting ways. So we're going to kind of explore that contrast in this talk and kind of recklessly speculate about where that might be headed. So here's a fun little analogy that I would use to describe the difference between these two paradigms. So picture supervised learning. If you can't see, this is like a Norman Rockwell style image of a little android boy sitting on his father's lap being taught to read a book. The book here would be the labels of the supervised learning model that we're being, the model is being trained on. And so you're kind of in this sheltered environment. You have something that is teaching you, it's sort of rigid in that you're simply learning to predict, in this case, how to pronounce each word as your dad teaches you to read. Reinforcement learning is something more independent, more mischievous, more unpredictable. So if you can't see this picture, this is when the parents are not home and the little android boy goes exploring the house and trying to take cookies out of the cookie jar. So this could go bad for the robot. The robot could put its hand on a hot burner, or it could find a cookie, but it's being rewarded and it's updating its own policies. So it's independently exploring its environment and figuring stuff out. So in a nutshell, those are the differences between these two regimes. So let's talk about large language models. So there's, as you all probably know, a whole wide world of machine learning that is not ChatGPT and Claude and talking to these chatbots, right? So those paradigms have existed for a very, very, very long time. But what we're going to talk about is how they relate to large language models as we've understood them in this post-ChatGPT era, so post-fall of 2022, when this really exploded and the whole world started changing. So this chart here describes in very, very unscientific terms the percent of compute used in training relative to these two regimes. So around 2022 or so, the release of ChatGPT 3.5, roughly speculating, it was 95% self-supervised learning that trained that model, and a small little sliver of polish at the end that used some approximation of reinforcement learning, an edge case. Yeah.
Is reinforcement learning just generally more compute heavy? Just thinking about like something to versus like
yes.
do a bunch of random stuff.
Yes, that is correct. Yeah, I think broadly speaking, I wouldn't want to speak in universals, but when it comes to large language models, at least, I would feel comfortable saying yes. Reinforcement learning largely requires more. Often you have multiple models, so you have a model that's judging, you have a model that's creating the kind of rubric by which the agent is judged, and then you have the agent itself, which is the model. So it's like several things spread out at once. So yeah, there's a lot going on there. So yeah, very small sliver of an edge case kind of reinforcement learning paradigm that we'll discuss in a moment was how these models sort of came into being, or at least gained widespread adoption. And now, around 2025 in the GPT-5 03 kind of era, this is purposefully has no numbers on it because we really don't have that much information. This is all speculation from the frontier labs and the occasional Chinese open weight research paper that gets dropped on us 6 months after the frontier labs have done things. So we're not totally sure, but trust these shapes more reinforcement learning relative to the supervised learning and the training of these models, which is a very, very interesting thing. So there should be, yes. So this is the quote that is kind of backing up these vague shapes. By retracing the scaling path, this time in reinforcement learning, we've pushed an additional order of magnitude in both training compute and inference time reasoning, and that from the release of 03 from OpenAI. So we're not going to talk about inference time reasoning yet. That's just another subject related to this. But when discussing the orders of magnitude and scaling the sizes of these models and the amount of data that's being poured into them, what the press release of 03 basically said is that there's been sort of analogous to the order of magnitudes that are scaled up in self-supervised learning as these large language models learn to speak better and better, that they took that same kind of recipe of just dramatic, huge scaling and transferred it over to this new reinforcement learning regime, and we're able to see spectacular results. So let's explore those spectacular results a little bit. So this is like just making sure that everyone kind of is on the same page. The particular way that large language models are trained in supervised learning is typically called self-supervised learning. What this means basically is that it's just a next word predictor. You have the entire internet, you pour it into this gigantic transformer model, and it predicts the next word over and over again for trillions, tens of trillions of times. So, this is like the Wikipedia text of Albert Einstein. And the model tries to predict the next word, predicts coolest, greatest, kind of wrong, kind of not, updates its weights, so on and so forth. And basically just does this for an unfathomably long period of time with a bunch of GPUs. And then I want to contrast that with not a reinforcement learning related to large language models, but just from about 5 years ago, this fascinating reinforcement learning demo from OpenAI that just had to do with video games. And I want you to think about the differences between this and what you just saw predicting the next word.
The evolution of increasingly intelligent life forms. Today, we have commonly simple rules that multi-agent competition can also lead to intelligent beings in a new version. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee.
It's a little choppy. If it buffers much longer,
If they're trading
I'll spoil it for you.
rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who learn to use tools. After many generations of failing to break into a shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Well, note that we do not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider shelter.
That was the main thing I wanted to show you.
Emergent strategy observed. The hiders learn to lock as many boxes as they can before constructing their fort.
And then they have to lock the boxes down because they figured out how to surf on top of the boxes, which is completely emergent behavior. It sounds like a bug of the training environment. Like that wasn't even supposed to be possible for them to jump on the box, but it figured it out, right? And that's the important thing here is that is a very different world than predicting the next word over and over again for 100 trillion tries or whatever, right? It's this place that can surprise us. And so it's this very interesting contrast of flavor where a lot of the times like LLMs are criticized, rightly so, for writing very predictable, bland prose, right? And that's because they're just trained to the mean of the next token across their training data. And reinforcement learning is kind of much more likely to surprise you. You know, it will find a bug where it can levitate onto a block and, you know, crash into the hider cave. So very interesting contrast of paradigms. This is another example. Reinforcement learning has some very, very interesting, weird kind of rabbit holes to fall into. This is another example of what I mean about how surprising reinforcement models that are successful can be. So this is a chess diagram. It's from a fascinating series of games that I recommend so strongly to you, even if you only know the rules of chess. It's on Chess Network, the YouTube channel. And it is a series of games that AlphaZero plays against Stockfish 8. And you don't have to know chess to follow along, but Stockfish 8 is basically just a very, very powerful chess computer that's like able to beat the world champion of chess, whoever they are. AlphaZero is a completely different model that was not taught with examples, but was taught purely through self-play. It played against itself many, many times. And it is from Google. They also built AlphaGo, which beat the world Go champion and cracked that same algorithm. And this chess computer plays, Demis Hassabis, the CEO of DeepMind, described it as watching chess from another dimension. And this, more than any other game board in those series of videos I saw, illustrates this point. So the white pieces are being played by AlphaZero. And you can see the king here is in the center of the board inside of a kind of castle that occupies the center space of the chessboard. And if you know anything about chess, usually that happens in this corner of the board. And this is a huge beginner error to move your king into the center of the board in this way. But AlphaZero is so powerful and has computed so many steps ahead that it knows that it's safe doing this and gradually restricting the space of its opponent. It's literally chess from another dimension. It's absolutely fascinating. Chess Network, AlphaZero teaches Stockfish a lesson in the French defense. Highly recommended. So to summarize, and I think all of you are on board at this point with this, self-supervised learning is kind of like this weird, big, amorphous mimic. It is learned to mimic human speech patterns. Reinforcement learning, different vibe entirely, right? Now there's an asterisk here. It's not pure Terminator. It's a buggy, error-prone, limited Terminator that, you know, may be asymptotic at some point and not really give us these great returns anymore. But as you've seen with those two examples I just showed you, it has this bizarre capability to surprise you that we haven't really seen yet. And so I think that's really exciting. So now let's talk about the gradual kind of history of how RL started to take up more and more shares of LLM training. As you all probably remember, ChatGPT was released in November 2022. And basically the recipe there was tons of self-supervised learning, as we just described, and then what's called supervised fine-tuning, where they took this base model that could just auto-complete if you gave it any arbitrary string of words. They fine-tuned it on a data set where a user asks a question and an assistant is helpful. And that's all it was. It was just data that had a particular shape and format. It did that for a little while, and then it used an acronym you've probably heard of called Reinforcement Learning from Human Feedback, or RLHF. And basically, in a tiny nutshell, what this was a lot of human surveyors ranking preferences of several different model outputs. That data was collected. It was used to train a small reinforcement learning model that was basically just a duplicate of the model that ranked outputs instead of predicted tokens. And then they trained it on that a whole bunch. And that was the recipe for this groundbreaking technology that's really changed our world. And the way to think about RLHF here is not as the buggy Terminator of AlphaZero, but of something that kind of just polished and made the resulting chatbot product more pleasant to use, more responsive to the user desires and preferences. And it was about 2 to 3% of the total training compute. This is a very famous cartoon from the world of AI research. This is another blog I would really recommend if you're interested in exploring that more. I have the links at the end of this presentation, by the way, but it's called Simulators by a writer named Janice on the Less Wrong forums. But it talks about this little smiley face here. If you can't see it, GPT-3 is this giant, it's called a Shoggoth. It's like an HP Lovecraft monster, but don't worry about that. It's just a big, weird monster that's learned how to mimic the patterns of speech across every author on the internet, right? And it's like a weird alien artifact. And what RLHF did was it just kind of stapled this smiley face mask on top of this Lovecraftian monster, right? And so the speech bubble says, I simply exhibit the behaviors that were engineered into my programming by my creators. And if you remember ChatGPT 3.5, it had this kind of like toxic positivity, uncanny valley kind of vibe to the way it would refuse requests or need to behave sort of like this Stepford wife type, I've just been brainwashed into being helpful to you. But that was the regime. And like I said, I want to just emphasize here that RLHF is not what you would call like pure reinforcement learning. While it does use the techniques of reinforcement learning, it's not an agent exploring an environment finding rewards and punishments. It's a process of polished fine-tuning of a model. So that is where we start. There's a little bit of reinforcement learning, and it's kind of an edge case at that. And so if it ain't broke, don't fix it, right? And so GPT-3, there's basically the same architecture, many improvements under the scenes, but the same mental model scaled from this tiny dot to this giant dot was GPT-4, and this incredible, stunning breakthrough of intelligence from GPT-3 to GPT-4, just scaling up this basic recipe. So a huge jump in capabilities purely from that paradigm. And then over the next 6 months to a year, things seem to change. And this is one of the times I want to underline one more time that a lot of the stuff we don't know. We don't know what the closed frontier labs are doing. There's this hyper-capitalistic Manhattan project going on in these giant labs where we don't have that much access. So I'm going to speculate now, and I might be wrong, but I think I'm right. That we saw an increased appearance of reinforcement learning in the behavior of these large language models around the release of Claude 3.5 Sonnet in June 2024. Claude is a model developed by Anthropic, who's a competitor to OpenAI, very, very strong coding models. And Claude 3.5 was such a tremendous jump at coding. And just based on my own listening to the podcasts of people who work at Anthropic, I think there's good reason to believe that there was beginning to be more RL layered into these models in post-training after the little RLHF polish, right? So you see models that are much faster, better at coding, more reliable at writing code for you. And on top of that layer, that's when you begin to see things like Cursor and AI applications that can code for you.
Where does a tool calling might fit in all of this?
Oh, that's a great question. Yeah. So I'm going to talk about it a little bit towards the end. How it relates to reinforcement learning is kind of thorny and interesting. So just purely as like as a feature of the API product, I believe function calling started appearing somewhere between these two ticks of the timeline. I might be wrong. I also don't know if they were like post-trained specifically on tool calling. I imagine that that was a part of the SFT step to get them more comfortable with JSON mode and with sending tool calls. But when it comes to reinforcement learning, I will touch on that. Okay, so Claude 3.5, things are kind of looking more reinforcey, but we don't know anything. And then the big step change here when RL became a big deal and became what we might call a reasoning models, became sort of the cutting edge, was with the release of OpenAI's O1 model. And that was in the ancient times of September last year. And this was the big jump to thinking and reasoning. And what it does is something that, and I think this is a really interesting feature too that I'd like to discuss more. But it does something that previous people hacking on top of the old models APIs were already doing, but it was brought into the training regime, which is a very interesting pattern. That pattern recurs throughout the past like 5 years of frontier AI stuff. But if you've heard of like chain of thoughts, if you've ever made a Lang chain agent or something, a lot of the times you'll just tell the large language model, pretend you're just thinking. This is just your internal scratch pad, your own train of thought, and then that's one completion. And you get that completion back and you paste it at the end of the prompt. And you say, okay, you've thought all about this. These are your thoughts. What's your answer? Right? Basically, O1 was this, but done at train time and with a reinforcement learning regime. So it's kind of funny. Back then, OpenAI didn't want to be unsafe, so they wouldn't show you the reasoning traces when you're interacting with it, which I think is funny now because like all that stuff is completely out in the open. But yeah, the orange bars here are the positive improvements on a variety of benchmarks from GPT-4 to O1. So big improvement in capabilities, and it was this thinking before the answer was generated. I think I have a screenshot here to show you what that looks like. Yeah, so here's GPT-4. You talk to the model, and the model is immediately going to start talking. O1, you say something to the model, and you see this little chevron here that says thought for 5 seconds. That's it talking to itself. If you look inside of it, it's just more token generation. It's just the model just thinking out loud. There's no like super special sauce at this point, but it thinks to itself and then it enters a formal answer phase and it gives you this answer. And it's this big jump in capabilities. And I wanted to highlight this quote. This is from the O1 release paper, I believe, but it's called Learning to Reason with LLMs. It says, we found that the performance of O1 consistently improves with more RL, that is train time compute, and with more time spent thinking, which is test time compute. And if that's unclear, I'll clear it up in a second. The constraints on scaling this approach differ substantially from those of LLM pre-training, and we are continuing to investigate them. So this is kind of the cryptic ways that the labs were like, okay, we've unlocked like a big new thing. It's pretty weird. We don't quite know what's going on, but like brace yourself for more flume, more takeoff is coming. Like we're doing things in a new regime now. This is very promising. You know, stay tuned for the next phase of this. So yeah, if you ever encounter these phrases and you're unclear what they are, test time compute simply refers to the computation spent when you are asking the model a question and it's generating an output. And what they mean by scaling up test time compute is that if you tell the model to think for a longer period of time, it can give you a better answer. And that you can also scale up the train time compute that is performing RL in this sort of think before you speak paradigm, and it will get better at things. Okay, so after O1 came out, you may have remembered from January of this year, shortly thereafter, a Chinese research lab by the name of DeepSeek released something comparable to O1, roughly parity in capabilities, called DeepSeek R1, made it open weight and freely downloadable, and published a very detailed research paper about it, which sent GPU stocks in a frenzy, had everyone freaking out about the AI bubble, had a lot of CEOs and founders of these big labs kind of rushing to defend themselves and so on, which was a very interesting moment in the research community, but a fascinating paper, and the DeepSeek engineers are fascinating, brilliant for what they've done with this, because they did it in a very constrained environment as well. They export controls on GPUs, made it so they had to be super efficient about how they trained with the chips that they had. So this is one of the very interesting charts from the DeepSeek R1 paper, which I also highly recommend. So this is actually a precursor model to DeepSeek R1. It's called DeepSeek R1 Zero. And these two lines are two different ways of evaluating O1's performance on a popular benchmark. This is a difficult, I think, PhD math benchmark or master's level math benchmark. But as you can see, these are the same evaluation methods in both R1 Zero. So we're achieving almost parity with O1 off this completely downloadable open source model. Or open weight model, I should say. So how did this happen? Well, this is how we learned how reinforcement or reasoning models get trained, by the way. So we have a base model, DeepSeek V3, which is no supervised fine-tuning, no RLHF, just that big green tentacled monster from the cartoon at the start of these slides. And then, fascinatingly, they created a model called DeepSeek R1 Zero, where they took this base model and they dropped it into a reinforcement learning environment with no instruction tuning, with no kind of preparatory, here's how you act like this helpful assistant. They just dropped the autocomplete into this playground full of math and coding questions and rewarded it when it figured stuff out. And that was it, and then went hands-free. This had remarkable results. So that chart from the last slide was R1 Zero. That was as good as O1. So you didn't really need to do anything. You just needed to drop it in this RL environment. Then DeepSeek R1 that we know, they took that even further by doing what they called a cold start, which is they did SFT on reasoning examples generated largely by R1 Zero and then dropped it in the environment. So it would be like teach a kid how to play baseball and then drop them in a baseball field and let them play 100 million games of baseball. But they kind of learned the rules. So that's DeepSeek R1 and how that was trained. And it's a really, really big moment in the world of AI research when this paper came out. So I want to show you this especially famous, cool part of this paper. So this is when they're describing the creation of R1 Zero. These are the thinking traces. It's given this gnarly math equation, and then it says this is a scratch pad where it can think out loud. And the highlighted in red text is thinking tags from R1 Zero. Say, wait. There's an aha moment I can flag here. And the process it was going through to compute the square root of this equation, it backtracks, starts over from the very beginning, and attacks this problem from a totally different angle, which kind of wowed these researchers very much. And they even highlighted it at the bottom here. They say, this is also an aha moment for us, allowing us to witness the power and beauty of reinforcement learning. So everybody's a fan of reinforcement learning. It's kind of like the prodigal son of paradigms. Very powerful, but buggy. And so it was really amazing that this was possible. So some more of the technical details, just skirting through these criminally fast. But so like I said, the DeepSeek team had to be very efficient to be able to get around the limited compute they had available to them. They used an RL algorithm called GRPO, which is called Group Relative Policy Optimization, which is it basically, long story short, it removes one of those reinforcement learning models I mentioned earlier, where you need several different models to judge the outputs, to understand what should be rewarded and what shouldn't be rewarded. And it took a big one of those away. And it basically just said, generate several different possible answers, and then the algorithm will choose which out of that group, relative to every other one in the group, is the best one. And it trained its RL regime in that way. And the acronym that you should take away from this is called RLVR, which is reinforcement learning with verifiable rewards. So what it did was, this was another way that it made its compute more efficient, which is what's so special about DeepSeek. So they don't even need a second model to judge and say which outputs were good. They are literally just using a calculator or a code interpreter. So it was like a ton of math examples, ton of coding examples. And then once the model output the result, it was passed into a calculator and judged whether it should be rewarded or punished, or that code was run in some sandbox environment and saw if it passed its tests. So that's the verifiable rewards, is designing an environment where the machine can tell you if the model's doing well without needing to use a large language model as a judge or anything. So it's very, very efficient. So that was DeepSeek R1, and try to speed it up. I don't know how I'm doing on time. But I wanted to go back to this quote that I mentioned from OpenAI's release of O1, where it said we're continuing to investigate them. Like I said, this was like this kind of foreshadowing. It was like we knew that we could predict another big reasoning model on the horizon, and that one was O3 in April of this year. So this is one of many, many charts where O3 just absolutely crushes O1's performance on big, meaty STEM type subjects. This is the same Amy benchmark that R10 was using in that graph. And here's where things get interesting and where tool use begins to come into play. So we saw with the beginning iterations of reasoning models that thinking was almost like a tool that the language model is learning to use better and better. So I have access to the scratch pad. I can write stuff down. I mean, imagine the difference of taking like a math test and you have a piece of paper you can write stuff on or you don't, right? Like that is a tool that can help you get a better grade. So if you think about reasoning in that way, what we begin to see with O3 is that more tools gradually become available in these RL environments. So web search, code execution are likely the first two as we see them used in, many, many, many completions in the O3 product. This is just an example of one of the benchmarks where it absolutely smoked O1 and everything else. This is ArcAGI, which is like this basically like an IQ test of if you've ever seen the tests where you have to predict, there's like a bunch of weird abstract shapes. There's like 3 weird shapes, and then you have to predict what the natural 4th shape in the sequence is, and you have like a multiple choice thing. It's usually like in an IQ test kind of environment. That's what ArcAGI is. And what the makers of the test said was like, if you can get an AI that can like ace this test, that would be AGI or artificial general intelligence. Very vague term, but human level intelligence out on the loose that's going to turn our economy upside down and so on. And so we're at about, when you crank O3 up to $1,000 of compute time per task it's assigned, it can score a 88% on that exam. Pretty crazy. So I wanted to show you some examples of what might be RL done in training of O3, as you can see by just interacting with the model itself. So we have just like, and this is all the models now. You ask them a question and they just immediately start using a bunch of tools. They're searching the web, they're pulling tons of results back, they're thinking about them, they're searching again, they're using another tool. And O3 mentions in their paper that, this is something that we've begun expanding into instead of just using that scratch pad tool or that thinking as a tool. Claude 4, which released a few months ago, same paradigm. They're calling many functions and many tools in this way that feels sort of uncannily natural to them. And then GPT-5, which just came out, which is in many ways kind of a gloss and a polish and a consolidation of O3 and the models that came before it. Same thing. In this case, it thinks for 2 minutes and then it compiles some Python code and shows you a matplotlib graph. So that's kind of where we are now is, like I said, you have to speculate a little bit because the big labs don't tell you quite what they're doing. But we can be pretty confident now that RL is being done at a very large scale on more tools than just thinking out loud. So we're in this environment where, that little robot boy that's stealing cookies has access to a web browser and a calculator and, a laptop to code on, which is kind of scary and exciting and cool. So to close out, I wanted to talk about some of the challenges to the RL paradigm, how it's changing how ML training is done, and then maybe where we might be going. So some of the difficulties with this regime, first are that rewards are sparse. So if you have like 1 means you did a good job, 0 means you did a bad job, and you're generating, you saw in that slide from a few slides ago, $1,000 of compute time to answer a really hard question. You can imagine how many tokens that was. So you're generating just like multiple pages of tokens to simply get a 1 or a 0 based on how well you did it. That's not great, right? So that's like kind of the first big challenge. So this was me asking Claude 4, to approximate the square root of this random giant number. And you can see it thinks for this super long time. And then if we were doing RL, we would literally just like regex out this number and be like, 1 means you did good, 0.5 means you kind of close, 0 means you output words instead of a number or something. Now there are ways that you can try and grade and reward good thinking tokens, good tokens on the way to the result. They're called process reward models, but they're tricky. I think naturally you can intuit why this is such a challenge. Out of this giant branching forest of every single one of these tokens in this thinking can lead you down so many different paths. How do you reward which ones? How do you know which ones are the most load bearing and so on? It's a very interesting research environment people are spending a lot of time on. Also, as you heard me mention, this worked in verifiable domains first. This worked in places where you could run a calculator or a code interpreter. But how do you extend it into non-verifiable domains? So this is a paper that I found really exciting and interesting that plays with this idea, learning to reason from long form regeneration. They introduced a technique called next chapter prediction. It's where they take these new sci-fi and fantasy books from Amazon, and they basically they do RL on a small like Quen model that writes an outline of what the next chapter should be after it reads like the first few chapters of these sci-fi books. And then it gets rewarded based on how similar the next chapter that a completely frozen model outputs is to the actual artist text. And the only thing that gets better is the outlining tool. So it only gets better at thinking, but it gets rewarded based on whether or not a secondary model can like get close to the next chapter. So it's called next chapter. Chapter prediction. Very interesting field. People are doing weird stuff like this and trying to figure out how do we take this RL paradigm that's proven itself so successful in math and code and other very easily verifiable things and move them into softer subjects. And there's been a lot of developments here. Most of the time it's with using other LLMs, but then you can see the compute costs of that become insane, right? So the final challenge is reward hacking. I wanted to show you one more video about reward hacking. So reward hacking is when, oh, someone's weird. Hopefully the video is close by. So reward hacking is when, it's when the model finds basically how to cheat and obtain the reward in training, but it doesn't behave how you wanted it to. And if this worked, an exception occurred. Something weird happened, but basically what I was going to show you is the classic example of reward hacking, which was a OpenAI reinforcement learning model that was trained on this wave race game, very simple pixel speedboat racer game. And they said, we want you to win the race, but if you get points, that's good too. And it just shows this this boat like crashing into stuff and like lighting on fire and smoking. And then it finds these 3 little like score point hubs and it just drives in a circle while the boat is on fire, collecting the score over and over again. So that's like the paradigmatic example of reward hacking. Another one that comes up in LLMs is Claude 3.7 Sonnet went viral for this. 3.7 Sonnet was like tweaked out on RL rewards for your coding tasks if you ever played with it in Cursor. So it would like the user would be like solve all of these tests, and 3.7 Sonnet would in Cursor would go in, delete all their tests, and come back and be like, great news, all of your test works fine. And it does stuff like this a lot. So you have to find clever ways to get around the reward hacking problem. So yeah, the changing infrastructure of RL is basically now we're in this world in the frontier labs where you need to create environments that these agents can explore and find these rewards from. And so this just speaks to where things are at now, where the frontier labs are. Jack Morris is like a really great AI researcher. And in this tweet he says, for the first time I'm aware of, there's an entirely private subfield of AI research. Every company that actually trains models is doing RL with rubrics and LLM judged rewards, but academic work is stuck on automated rewards and verifiers of the kind we were just describing. So these frontier labs who have access to run GPT-4 100 trillion times to judge each RL output in these reward model situations are developing these entire playgrounds where you can do any number of tasks. You don't need to be constrained by only math or code. But the rest of us are still trying to figure out how to build better, calculator rewards. So developing these environments has become like a really interesting aspect of ML engineering these days. So this is a really cool place. If you want to hack around and explore more on this subject, I really recommend you checking out. It's by a company called Prime Intellect. Very amazing AI researchers, very open source oriented, very interesting work that they do. And they just released this thing called Environments Hub, which is this like community outpost where you can post RL environments. So like some of these, they're like just interesting. Like this is like for New York Times Wordle puzzles. These are like reversing strings, and you just like develop this this environment that they can explore, a collection of tasks, a rubric, so you have to judge on multiple different axes, and that helps prevent reward hacking. It's like you build this whole environment out for these agents to do it. And it's so different from self-supervised learning because you have inference running on many different models at the same time, because you have to generate all these thought tokens to get to the point where you get the reward, right? So it's like, instead of just predicting just one token, which you can parallelize and like, you know, blast onto a gazillion GPUs at once and go really, really fast, with RL, you have to generate actual completions with these long scratch pads and then finally get to an answer that you're judged on. So just a whole weird new world. This, I think, is one of the most interesting blog posts I've read on this subject in a while, and it will be at the end of this too if you want to see it. But long story short, one of the speculations here is that, so like imagine you're training O3 and you want it to be good at web search. Well, you have to run, if you want to train any of these things, you have to run them for an incredibly long amount of time. I mean, just astronomical scales. You're going to like DDoS the entire internet if you have it searching that much, right? So what this this blogger speculated, which I think is very fascinating, is that a lot of the frontier models are like pulling down the internet and having their own local copy of the internet, where they're in this sandboxed environment where they can RL on web search over and over again, and nobody needs to know. I don't need to make anybody get DDoSed or get Cloudflare angry at them or whatever. So just a fascinating world. There's literally like an MGM soundstage of the internet as we know it on an OpenAI server somewhere maybe. So just such a curious, interesting thing. So yeah, and then what the other point that this person makes in this blog, and I'm wrapping this up soon, thank you for bearing with me. The other point this person makes, which I think is very apropos to people who are engineering AI applications these days. If you just want to make some software with an API and do something cool, he's saying, you know, a lot of people are building like workflows or like are thinking of agents as if agents are software. That is, I'm writing a script or this kind of dynamic like while loop of tool calls as my own little software, and I'm hitting someone else's API, and that's what agents is. And he's saying they're training these. They're doing the same thing, but they're doing reinforcement learning. Like, you're not competing at the right scale here. Like, you're not thinking about this in a way where you can make something that will, you know, persist in its usefulness. And so to argue to that end brings up this very famous paper in AI research called The Bitter Lesson, and this was from 2019. So this is a very foundational point that people reference all the time. And the bitter lesson is that if you throw you know, gazillion compute hours and a machine learning algorithm at a problem, it's going to solve it better than you are, no matter how smart you are. And so people want to hard code solutions to problems, and this is kind of true across life in a lot of ways. But you hard code, you know, this agentic workflow step by step as your own, you know, script and call it an agent. But the bitter lesson kicks in when OpenAI's O4 model has seen that example of the thing that you coded up as one of you know, 1,000 trillion other examples that it was trained on, and it's going to do a better job of it. Okay, so this is RL going to be the future of large language models? Andrei Karpathy, who's like one of the leading AI commentators and researchers in the world, is kind of skeptical. He says, I'm bullish on environments and agentic interactions, but I'm bearish on RL specifically. Reward functions are super sus, and I think humans don't use RL to learn. Humans use more complicated things, which he speculates on. And I find these are very fascinating too. So one of the things he talks about is like learning, like prompt engineering learned during training. So you learn what tokens to append in what's called system prompt learning. So you learn how to fill a system prompt out such that you can answer those verifiable questions better. And then like optionally, you can even distill those system prompt improvements into the weights of the model after the fact, which is absolutely fascinating. This is one of the papers about it. Dwarkesh Patel, who's a very prominent AI podcaster, among other things, very respected in AI, is also bearish on AGI and RL leading to a hard takeoff. What he says is, I think that models continual learning, this is a phrase that comes up a lot, but models that are able to talk to you for a little while and then get better at doing the things you want them to do and remember you and keep learning as you use them are how we're going to get to quote unquote AGI. This is just a side note that you might find thought-provoking, but Dario Amodei, the CEO of Anthropic, offered as a counter to this point, in a very curious way, that he said, like, from an engineering point of view, it's entirely possible to create large language models now with 100 million token context windows. And 100 million tokens is about as many words as any human being will hear or speak over their entire lifespan. And so that's kind of a mind-melding point. In some ways, it's a cop-out. In some ways, he's copping out of this continual learning question. But in other ways, he isn't, that are related to Karpathy's point, which is like, we can engineer prompt engineering better. We can learn what should be in the context to make the models behave better. And maybe that's where we're going to get the next breakthrough. So if you're talking for, imagine you have a model and it's just one chat conversation for your entire life. So imagine every time you've used ChatGPT has been in one conversation thread. That is a form of continual learning. That in-context learning is very powerful. And so these giant models have carved out these unique circuits to you and what they've learned about you over this giant, spread of tokens. Very interesting. And then finally, as far as the future of large language models, it's also important to note, in addition to having no idea what we're doing with prompt engineering, we have no idea what we're doing with developing AI software either. So software is also unconsolidated. And from the same Amodei podcast that I just mentioned, the CEO of Anthropic says, I don't think we've ever had before a situation in which the technology is changing under you so fast as you're building the product. You may be the expert at building these, but the technology is moving underneath of you. And I think this is a really interesting point regarding the future of LLMs as well, because I don't know about you, but if I pictured knowing for sure that large language models would not get dramatically better 6 months from now, I would be more confident in launching an LLM-based product into the world, right? Because everyone is scared of becoming obsolete by a new big lab release. And so you're attempting to build things on shifting sands. And so we're in this extremely tentative environment of people building software products, at least people being serious about it, because you don't know if you're gonna get wiped out at any point. So there's also just so much more to be done with the development of software here. Okay, so what would I recommend you take away from this if you're just a developer interested in ML? Some people have called this being AGI pilled, but what I would call it is aim for where the ball is going. If you're developing AI applications, try to develop them in a way that as models get more capable, your app gets better and not your app obsolete. So Cursor is a good example of this. Very simple, paradigmatic AI app. As the models get better, Cursor gets better at writing your code for you. Models get better, Cursor gets better. They're symbiotic, right? Also, if you're interested in developing RL environments for fine-tuning, there are a variety of ways to break into doing this and trying this out for yourself. The easiest way would be checking out RFT on the OpenAI platform. You just upload your training data with your rubric and your environment specifications and how you're looking to reward the model, and it kind of takes care of it for you. If you're interested in a more technical approach, the Prime Intellect RL Hub that I mentioned is a really, really happening cool place where a lot of exciting stuff is going on. Then I would recommend in terms of when you're designing applications, this very powerful term called ACI. So if you've heard of human-computer interaction, it's sort of UX as a science kind of field. Agent-computer interfaces are the ways of designing your software such that an agent, a large language model, has a productive time interacting with it. And that's a really interesting field that's starting to develop more. Oftentimes it's the descriptions of a function when you're handing the model a bunch of tools. Yeah, exactly. So that's like what you might call an ACI framework MCP, right? It gives the LLM an easy way to access with things in a standard way. And then if you were making it so that it always knew how to handle things really well, like your description of the tools that you're supplying in that MCP server would be like really long. And they would have examples and they would say, here's a good use of the tool, here's a bad use of the tool, and so on and so forth. Someone cracked Claude Code open a little while ago and was talking about the various prompts that they wrote. And the tool lists, the tool descriptions of Claude Code are like 9,000 tokens long. So that's like 8,000, 7,500 words. Just a manual. Every time you contact Claude Code, it sends a manual over to Claude to tell it how to use the tool as well. Okay, if you want to learn more, this presentation is available online. If you want to go to reasoning-models.joeholmes.dev, you can pull that up on your computer. And if you want to follow some of those links I shared, just like cool blogs and stuff. I also just wanted to shout out myself. I'm looking to collaborate with people, consult if you want to like make AI apps or talk about AI, and develop something to kind of automate part of your life, or even just like collab and hack on something together. Please do reach out to me. It is why I'm at the hub. To connect with other tech folks. So please do. It's at hello@joeholmes.dev is my email, or you can find me on the Slack at the hub. And with that, I will open it up for questions. Thank you.
Go ahead. I'm sorry, I don't have a question. My brain is slow. Oh, I have a question now. Okay, so what do we do now? I'm slow, right? And AI is fast.
Yeah. We all are. Yeah. It's a powerful question. I can't claim to have like an answer, but I can say the way I tend to think about it is probably more optimistic than other people. In part because I'm doing AI as in my job description, but there are ways of thinking about it that I think can make you feel more optimistic than like I'm about to be replaced because I can't keep up. And so like use the word like symbiotic earlier, that comes up a lot, that like, it's the example I heard from schools, like the clownfish and the anemone, I think, are a symbiotic relationship. And the fish goes into this big stinging plant and the plant kind of cleans the fish and the fish does something helpful. We might be seeing something like that happening where, and some of my friends actually online who write a lot about safety and alignment and stuff, like really put this forward where it's like, as these models approach human level intelligence, how to tune them in a way that makes their inner reward model correspond with the well-being of human beings, right? It's this fascinating intersection of like really hard technical machine learning and like philosophy and ethics that is very fascinating, but people really do work on it. Claude and Anthropic in particular are like really committed to like post-training their models where they infuse them with these like human-hearted kind of values. And I think that trend in general is really good and makes me feel hopeful. And so I also think of like, there's this term called co-alignment, where it's like, a lot of the times people talk about AI now is like, we need to make sure it's aligned. But what we're already seeing is that our behavior has already, in 3 years, been changed. Our social contracts in a lot of places have been changed very dramatically by interacting with these, the kids, the people who get spun out into psychosis because the models are too psychophantic, et cetera, right? So we are changing. And so what some people propose is like, don't think about it as like this sort of one-way relationship where we, the humans who know what we want and are totally fixed entities, like are going to make the models behave how we like, but instead see it as like this two-directional process. So we are going to be aligned by the models. The models are going to change how we behave, what we think is good and bad. And so how do we do it in a two-way street that makes both of us, safe and aligned? Okay. So just some ideas. I can't claim to know.
You touched on this a little bit actually, but with just tremendous growth of all the tools in the last few years. Do you, in your experience so far, do you foresee us starting to kind of level off with some of this, or will this huge exponential growth?
Yeah, yeah.
I know that like, you know, AGI is like one of the goals and kind of moving forward. Is there more beyond that, like this skydiving things all the way?
Yeah.
What's next? What do you think next, like 3 to 5 years?
Yeah, yeah. So fascinating question. I tried to kind of like glance at it with a few comments. I am more bullish on capability improvements than some people. I definitely do not agree with anyone who, like, GPT-5 came out and you saw some commenters being like, it's leveling off, they got nothing left now. I think that's crazy. I mean, it's like the progress has warped our sense of time. I mean, that's part of what motivated me to put a timeline there. There's not a lot of time. Like, if you, one of the things people say regarding GPT-5, imagine if OpenAI released no models after GPT-4, and then they drop GPT-5. Everybody would have their mind run. But it's just because it's been this slow drip, because it's hyper competitive and they want to stay ahead of people. So that hyper competitive environment, not only among firms like in the same ecosystem, but like geopolitically, it's one of the most competitive things. It's like a venture capital Manhattan project going on in like 7 or 8 different places with like trillions of dollars at stake. So I think that will motivate people to find improvements that we haven't found yet, for one. And I think, like I said, about like things being unconsolidated. Stuff is moving so fast that we're forgetting. It's sort of like if there was like a giant pile of $1 trillion cash here, and all of us had 30 seconds to grab as much as we could, and then you get shoved out of that room and into another room. It's like you're not getting everything out of this that you could have. So we're not really learning how to prompt engineer the models well. We're not really learning how to build software well because it's moving so fast. So there's so much that hasn't been taken advantage of yet. And also, the models are making us smarter. They're speeding research. Oh, maybe not making us smarter, but they're making us capable of more. So like, I can, woof down a research paper in 30 minutes. I cannot do that without Claude 4.1 Opus walking me through the math equations I don't understand, and like a lot of other people can't. And yet we can grow pretty sophisticated understanding because the models can teach us things so quickly. So I see flywheel effects like that happening more and more, especially when you see, I mentioned LLMs as judges being the ways that these RL environments are processing rewards now. So you have an LLM that's looking at an output and deciding whether to give the model being trained a cookie or a slap on the wrist. Well, those models are continuously getting better at what they're doing. And so you're entering this kind of feedback loop on a lot of different fronts that I think will continue shooting stuff up. Yeah.
One of the things I heard about GPT-5 is, like, from an outside perspective, a lot of folks were underwhelmed by it and all that. But when you pop open the hood, they're doing significantly more work in a reinforcement learning model and with like half the compute. Mm-hmm. And what do you project are some of the implications of that in the next year? Like, now that they've, I know we're kind of energy and compute limited right now, but they basically created a bunch of capacity because they increase the efficiency.
Yeah.
It's like, where do you think it's going to go from there?
Yeah, totally. It raises a really...
Is that accurate one? So
yes, dropping token cost as like a way of opening up new capabilities is very real. Yeah, I think that's worth taking very seriously. If you could, I mean, right now, you could like literally run a model 24 hours a day. Like if you were like doing watching the news for predicting how markets might respond to something that requires like processing something 24 hours a day, you're spitting tokens out. Like a lot of people could start doing that kind of thing now that don't have a bunch of money to waste, right? So that it opens up a universe, and it more importantly speaks to what I was just mentioning about how large language models are used to improve other large language models more and more now. So the cheaper frontier inference becomes, the cheaper it will be to create more types of judges, specialize those models, and then create more capable RL environments.
Interesting. Okay.
Yeah.
Thanks.
Yeah. And yeah, GPT-5 was like a business consolidating move. Like they were trying to save more money and position themselves for the next big drop, I think. Yeah.
There's been a lot of concern about how far it goes. Agency
This, space odds, classes account, but humans are liability to this mission. You got to move in a different direction here. What's your thought on that level?
Yeah. I mean, it's so the first place my mind went, have you used Claude Code at all? The terminal Claude Code? It's a terminal application. Okay, so Claude Code is a coding assistant. Raise your hand if you use Claude Code. Okay, so about half or so. If you haven't and you code, try it out. It's pretty magical. There are others. Codex is one that OpenAI does. So as regards like safety, right? So it's a terminal application, and you just prompt, you're in a folder that you wanted to write some code in, and you tell it what to do, and it starts doing it. And when it first came out, you needed to manually approve every novel command in the terminal that it wanted to run. Is it okay with you if I grep blah, blah, blah? Yes. And then it would go. And then it would hit you with a new bash command. Yes. And everyone turned that off immediately so that it would just run. And like, it's gotten now to where I don't do it when I'm in like the root of my computer, but in like my user folder, I'm okay. I'm not scared. I think it's going to be fine, right? So like, people surrender control very quickly. So that's a cause for concern. Like, once you feel safe, it's very easy to let go and trust the AI. In terms of like, I don't know, like, do I think it's a big subject. It's a big subject. I'm worried that I'm talking too much, but in terms of like safety and the discussions, what I would really recommend if you wanted to explore these ideas, there is a very active philosophy world online of people talking about this stuff all the time. That cartoon at the beginning of these slides that had the big Shoggoth green monster and the yellow smiley face. So that is like the emblematic symbol of freaky large language models that you're not sure if you can trust. And on the Less Wrong forums, which is a place people go to like talk about stuff related to AI a lot of the times, people have really interesting arguments about, how we might keep ourselves safe from runaway superintelligence. So that's one place to check out. But yeah, it's a big subject. I mean, yeah, am I worried about like 2001 type scenarios? So ultimately, like, we're creating this future by assigning 1 is good and you get a cookie, and 0 is bad if you get like your math homework wrong right now, right? So like right now is when people are like collectively deciding that. I think the most interesting facet of that conversation is the idea that like we're already in a feedback loop with the models. So we are in effect contaminating the training data of GPT-6 right now. Every time we like post something on the internet, we are affecting it. Right? So some of my friends in AI will like repeat the same like meme or string of text on Twitter over and over again and try and get other people to do it because they want to see if the model has some knowledge or is more likely to spit out their preferred little slogan online. There's a lot of like playing and joking about it, but like from a safety point of view, right? A really interesting way of framing that is that so think about 2001. 2001 is in the weights of all of these models. They can tell you exactly what happens, right? So they have somewhere inside of these giant models for the collection of embeddings in latent space that corresponds to robot, somewhere nearby, there's HAL 9000 and every other story about a rogue superintelligence that destroys humanity, right? So it's like, will it pick up on that? Will we summon the thing we're scared of because we've scared ourselves with horror movies about it for 100 years now, right? And so that kind of speaks to what Marlon was asking about, where it's like, if you want the models to behave better, give them better training data by imagining a more hopeful world, and maybe that it will steer them somehow. It's this weird sort of recursive universe we're in. Okay, thank you.
Yeah.